Okay, welcome back. These are the notes for Pre-Calc section 5.1 day 3. We just have two more main examples to look at. The first one involves solving a trig equation with our calculator. If you think back to what we did yesterday, we were solving all of these trig equations, but just by hand because they all worked out to be nice angles that were on our unit circle. That isn't always the case. So grab your calculators, and the first thing I need you to do is to go under your mode and change it to radians. You want to be in radian mode. Okay, and it's asking for where is the cosine of x equal to 0.7. Well, we know a few things. We know that, for example, the cosine of x could be 1/2. We have that value on our unit circle. All right, at things like pi over 3s. We know that at 45 or pi over 4s, our cosine is √2 over 2. And if we looked at a decimal equivalent to that, it would be about 0.707. So that's really close to what we want. But we want the cosine of x to be 0.7. So we know it's going to be somewhere around pi over 4 or 45 degrees. All right, so what we're going to do is we're going to graph the two sides of this equation as two separate equations. So enter in your calculator for y1 equals the cosine of x. That's going to get us a cosine curve, and because we have it in radian mode, it will look like a cosine graph, which is our blue graph over here in our picture. All right, and then our second equation is our 0.7, just y equals 0.7. That would be our pink horizontal line in our picture here. And we're looking for where they intersect. So go ahead and graph it and then find the intersection point. There are two of them. There is one that is in a positive section right here, and there's one that would be a negative value right there. So go ahead and pause the recording and do your calculator intersect. Okay, so when you solved this using intersect, you should have gotten x values of both a positive and a negative 0.7954. If we converted those into degrees instead of radians, we would get 45.57 degrees. So again, it's really close to what we were saying over here, where x should be around 45 degrees. Okay. Now, it does say to find all the solutions, not just within one rotation around our unit circle. So keep in mind that every time we add 2 pi to this, we get back to the same values for cosine. So our final answer here is that x equals a positive or negative 0.7954 plus 2n pi, where n is an integer. Okay, that's going to get us all of the different. In other words, if we kept this cosine curve going, we would keep intersecting that value of y equals 0.7. Okay, our second example here, cosine squared of x equals 0.4. So again, we can solve this using our intersect feature. So y1 equals cosine squared of x, y2 equals 0.4, and we want to look for where they intersect. All right, now when you enter this on a calculator, you're actually going to be entering this as the cosine of x squared on the outside. Okay, that's how your calculator is going to read it, but it means the same as saying we're taking the cosine of x and squaring that whole thing. We're not just squaring the x. So make sure you have that in parentheses. All right, so go ahead and graph it. Again, be in radian modes. And we are looking for that intersection again. So we should get two values, a positive and a negative 0.8861. And then again, if we continue to add 2n pi to it, we keep going around in either direction. Our third example says the cosine of x has to equal 1.77. And if you think about what our graph would look like, before we even graph this, remember cosine starts at 1 and it goes to 0, then -1, back to 0, back to +1. right, within a space of 0 to 2 pi. Well, it's asking for where we hit a line at 1.77, and we're never going to hit that. So we don't even have to bother typing this in our calculator. There is going to be no solution for that. We've talked about the range for cosine being from -1 to +1, and that all of your values bounce between +1 and -1. All right, our last example, we have two expressions, and it's asking us to do a trigonometric substitution. And then it says use Pythagorean identities to write the resulting function as a multiple of a basic trig function. All right, so we've got the square root of x squared minus 9, and they are asking us to replace x with 3 secant theta. So we're going to dump that in there. Okay, our second one says we have the expression the square root of x squared plus 81, and this time x is supposed to equal 9 tangent of theta. So we will be dumping that right in there. Now, one thing to pay attention to, if you take the square root of x squared plus 81, you can't square root those two pieces separate and just say that's x plus 9. That doesn't work, okay? So we are going to do our substitution, and I'm actually going to do part B first. It's a little easier substitution. So let's dump that in. It gives us the square root of something squared plus 81. Okay, and we are substituting in place of an x 9 tangent theta. Okay, now that needs to be squared, so we're going to end up with 81 tangent squared theta plus the original 81 that was in there. And if we think of factoring, we can take that 81 out of both and say it's times tangent squared theta plus 1. Okay, if we just factor it. Now, look at your Pythagorean identities. Tangent squared theta plus 1 is equivalent to secant squared theta. So let's do another simplification here. 81 secant squared theta. And now notice it is all one term, and we can square root that. So the square root of 81 is 9. The square root of secant squared would be secant. And the only thing that we have to make sure is, let's put some absolute value bars around that, because we cannot square root if that was a negative value. All right, let's go back and do part A. We make our substitution. We've got the square root of something squared minus 9, and we are dumping into that 3 secant theta. So now if we square that, we have 9 secant squared theta minus 9. We can do another factoring step where we pull that 9 out from both. That leaves me secant squared theta minus 1. And if you think about the Pythagorean identity that we used in this one, we said tangent squared theta plus 1 is equal to secant squared theta. So if we subtract 1 from both sides, all right, secant squared theta minus 1 would be equivalent to tangent squared theta. So this becomes the square root of 9 tangent squared theta. And again, we can square root that now and say we get 3 times the absolute value of tangent theta. All right, and that is it for our notes for this section. All right, so day 3's assignment is again on page 410, starting with question 57.